This video is about transformations and specifically a horizontal stretch or shrink. And for our notes, of course, we'll recall before we get going with this that we've been working with a lot of parent functions. So when we see y equals f of x in any specific transformation, we're referring to any of the parent functions. There are five basic ones we're working with right now. And so those will, of course, some of them will show up in the examples, but that's what we mean by f of x. Now, for a definition for horizontal stretch and shrink, we'll, of course, understand the basis of it to be where y equals f of c times x. Notice now the value c is tucked inside the parentheses in the input of the parent function multiplied in front with the x, or in front of the x. So if c is greater than 1, we're going to call this, or we'll see that this will turn into a shrink horizontally. Now right away, you may observe that that's the opposite of what we were discussing in the vertical direction. When we did vertical stretch and shrink, when c was greater than 1, it was a vertical stretch. Well, it turns out that when c is greater than 1, it's a horizontal shrink. So remembering that those are the opposites can be helpful. And then we say horizontally it can shrink by a factor of 1 over c. Now that's a little different as well. The 1 over c we were seeing as a factor of c in the vertical sense. So we'll see what that means for us practically in a moment, but take note that that's the definition. And then of course, if c is between 0 and 1, not including either one, we're going to do a horizontal stretch. Again, the opposite of what it was vertically. When we saw c between 0 and 1, it was a vertical shrink. But horizontally, it's a stretch. And of course, this is by a factor of 1 over c. And we'll see how that happens in just a moment. The diagrams can be helpful when looking at these functions, but I think specifically going step by step through some examples will be most useful. Now let's discuss, before we get to some examples, how the horizontal stretching or shrinking actually happens. What does occur that causes this on a graph? Well, graphically we're going to divide the x-coordinate of any point on the parent function by c, but keep the y-coordinate. So again, if you look back carefully, you'll find a lot of similar but opposite practices corresponding with the vertical stretch or shrink. Instead of what we were doing vertically, which was multiplying the y-coordinate by the c value, in this case now with the horizontal stretch or shrink, we're dividing the x-coordinate by c. Now if you look back up at our definition, we had a moment where we said by a factor of 1 over c. That was true for the horizontal stretch or shrink. The 1 over c factor will be taken care of when we divide by c. So we won't really have to worry about the 1 over or whether it's c. We'll just remember that for horizontal stretching or shrinking, we divide the x-coordinate by c, and that will do it for us. So, to note, if c is greater than 1, remember this is the opposite. In a horizontal sense, we're dividing by the x-coordinate, we're dividing the x-coordinate by c, and that would make it smaller. If you're dividing by a number that's bigger than 1, you're making something smaller. You're dividing by a larger number. This gives the appearance of shrinking horizontally, or in other words, shrinking toward the y-axis. Or if c is between 0 and 1, of course, we'll divide the x-coordinate by c, and that will make it actually larger. Now that seems a little counterintuitive, but dividing by a number that's between 0 and 1, such as 1/2, 1/4, anything in that range, dividing by a number of that type will actually make the result bigger. You might recall or imagine dividing by 1/2 is the same thing as multiplying by 2. It's reciprocal, so the number is actually getting bigger. And this gives the appearance of stretching horizontally, or in other words, stretching out away from the y-axis. Let's look at an example where we'll do several things. We'll identify a parent function. We'll graph the parent function using a dashed curve. We'll describe any transformations occurring, and then we'll actually perform the transformations with a solid curve to get the new function. Our first example function is f of x equals the cube root of 2x. Let's start by understanding the parent function of this one to be f of x equals the cube root of x. And we'll go ahead and graph this function, recalling the parent function. We have points at 0, 0, 1, 1, 8, 2, which will take us a little bit off our grid. We'll just extend to reach it. And then negative 1, negative 1, and then negative 8, negative 2. We'll connect these points with a dashed curve to get our parent function graph, which should resemble the parent function we started with in the introduction video to this. It's kind of like a stretched out S horizontally. So there's our parent function graph. Now, next, let's identify how this function is being transformed. If you look at the function definition, we find a 2 in front of the x inside the cube root. So that 2 is being multiplied with the x inside the cube root. Well, if we look at our definition, this means that the c value is 2. And we'll recall that produces a horizontal shrink. Look carefully at each definition, and it's good to review even the previous ones so you don't get them too confused. But when c is 2, it's a horizontal shrink when the 2 is in front of the x inside the function here. So that is conducted, as we saw in our notes above, by dividing each x coordinate of each parent function point by the number 2. We'll carefully look at each point and what happens. The origin has the point 0, 0, so if you divide its x coordinate of 0 by 2, you still get 0, which means it remains at 0. The point 1, 1, originally on our parent function, has an x coordinate of 1. If you divide that by 2, you get 1/2. That will move the point to be now 1/2, comma 1. And then the point that was 8, comma 2 had an x coordinate of 8. We'll divide that by 2 and get an x coordinate of 4 for a new point of 4, comma 2. And then if we follow the same practice going to the negative points, negative 1, negative 1 will turn into negative 1/2, negative 1. And then negative 8, negative 2 will turn into negative 4, negative 2. And then if we connect these new points, which I've now drawn in red, with a solid curve, we'll see a very similar shape. Now, drawn by hand, it's a little hard to see sometimes how the shrinking takes place, but it is shrinking in toward the y-axis, which is what we said in our note. That's how the shrinking occurs. Let's look at a second example. This time our function reads f of x equals the absolute value of 1/2 x. And so we'll go through each part, first identifying the parent function. And given our list of options, the absolute value of x matches our function the best. For part B, we'll go ahead and graph this parent function using a dashed curve. So we'll recall several points, 0, 0, 1, 1, and these points step upward. They slope 1 in the positive direction. Or we could do the same thing going left, negative 1, 1, negative 2, 2, going with a negative slope, climbing upward and leftward. So there's our parent function. Now, we want to describe the transformations occurring in our example. We'll notice the 1/2 that's written and multiplied in front of the x. So take note, if we go back to our definition, this means that the c value is 1/2. From our definition, we'll recall that when c is 1/2, we end up with a horizontal stretch. And so how do we do that? Well, again, we'll divide all of our x coordinates of all of our parent function points by 1/2. But dividing by 1/2 really means multiplying by 2. Let's keep that in mind. So now let's go over to the graph and conduct our, in this case, stretching by dividing all the x coordinates of all of our points by 1/2. Now, dividing by 1/2 really means multiplying by 2. So the point 1, 1 is going to turn into 2, 1. The point 2, 2 will turn into 4, 2. and so on. 3, 3 would turn into 6, 3. Of course, the origin stays right where it is. It's already on the y-axis, so stretching it away from the y-axis by a factor doesn't actually change anything. We'll go ahead and adjust or stretch the points on the left side of the y-axis as well. So the point negative 1, 1 will turn into negative 2, 1. Negative 2, 2 will turn into negative 4, 2. And negative 3, 3 will turn into negative 6, 3. If we now connect our new stretched points with a solid curve or line, we'll get the stretched out, horizontally stretched out version of our absolute value parent function.